One of the key portions of the AP Calculus test is analyzing graphs, and especially analyzing graphs that aren't of the function itself. So we're going to look at a function here and talk about what we can read from it, whether we have f of x, f prime of x, or f double prime of x as what's actually being graphed. So what they're going to ask is they're going to give you a graph and they're going to say find the critical numbers, points of inflection, increasing, decreasing stuff of the function f of x. Now, if the graph they give you is f of x, like it is in this case, this is really easy to find. So, first off, we would look for critical numbers. Critical numbers are points that would be maximums or minimums when we change from increasing to decreasing. So those should be pretty easy to spot. A maximum occurs at x equals negative 3, or that's a minimum there. A maximum occurs at x equals negative 2. And a minimum here at x equals 4. Those are critical numbers because they go from increasing to decreasing or vice versa. Okay? Let's skip down to those increasing, decreasing areas. So increasing, when is the graph going upwards? That's all we have to look at. So the regions there would be from negative 3 to 2, and another region would be from 4 up to infinity. That means my decreasing regions would be the other ones. So negative infinity to 5, negative 5 I should say, because I'm going down. And then also going down from this max at 2 to that min at 4. So 2, comma 4. So the increasing, decreasing regions should be pretty straightforward to find as well. Now, points of inflection are a little bit tougher to see. Remember, that's when you change from concave up to concave down or vice versa. So concavity means like smiling. So smiling up, smiling down, frowning, smiling up again. Well, this definitely looks like a point where I'm changing from a smiling graph to a frowning graph, curving upwards, curving downwards. So x equals 0 would definitely be a point of inflection as far as this graph goes. Now, as for when I changed from this frowning back to smiling again, it appears like right in here around x equals 3 is where I changed. So in this part, I'm curving downwards, and then I start curving back upwards again. That one's a little bit tougher to see. It would be just somewhere around 3, and they would ask you to approximate it if you're looking at a graph. So that means concave up, when is it, when you have a smiling looking graph, starts at negative infinity all the way to your point of inflection of 0, and then from the next point of inflection 3 all the way up to infinity again is when it's curving upward in this problem. It's curving downward, concave down, from 0 to 3, this frowning part in the middle. So again, if they give you the function f of x itself, it makes it pretty straightforward to see exactly what we have. However, let's look at this exact same graph, but now we're given that the graph is of f prime of x, the derivative of the function f. And we want to find when the function itself had critical numbers, points of inflection, all that stuff. So we're going to have to look at things a little bit differently. Remember, a critical number occurs when the derivative equals 0. Well, we've already been given the graph of the derivative. So we have to look, when does the derivative equal 0? Well, it would equal 0 whenever it crosses the x-axis, or whenever it touches the x-axis, I should say. So critical numbers can occur when x equals negative 5, x equals 0, and x equals 4. Now, if you want to even look further, we could call whether they are maximums or minimums. Remember, max means you're going, the derivative changed from positive to negative. Minimum would be negative to positive, and if it does neither, then it's neither a max or a min. So let's this one here, we change from positive to negative, increasing to decreasing. That would make this guy technically a max. At 0, I went from negative to positive. That would make this a min. And at 4, well, I went from positive, leveled off a bit, and then went positive again. So this is neither a maximum nor a minimum. So this actually would not be any extrema at all. This would be what we call a saddle point. So it is a critical number, but not any extrema whatsoever. Okay? Increasing and decreasing. We kind of just talked about this as well. Increasing means that the derivative is positive. That means that in terms of this graph, because it is the derivative itself, we need to look at when it is having positive function values, positive y values, meaning it's above the x-axis. So those regions would be from negative infinity to negative 5, because that's when I cross to go negative. It'll also be from 0 to 4, and then also from 4 to infinity. Those are the regions when I'm above the x-axis. Okay? Decreasing then would be when the function is negative, or the derivative, the function that we're given here, is negative. So that's going to be from negative 5 to 0, because again, decreasing means the derivative is negative. All right, let's look at points of inflection now. Points of inflection occur when f double prime equals 0. Well, let's think about that. F double prime would be the derivative of f prime. The derivative means slope. So I need to know when the slope of this graph we're given equals 0. Well, that's going to occur at maximums and minimums on this graph. So my points of inflection will occur at 3 spots. At negative 3, positive 2, and positive 4. Okay, concave up and down. That means that the second derivative is positive or the second derivative is negative for those concave up and down. Concave up means curving upward. The derivative, or I should even say this is f double prime, which is the derivative of the graph that I'm given. So that means that the derivative of the graph I'm given must be positive. The slope must be positive. I must be increasing. So what regions am I increasing? That would be from negative 3 to positive 2, because this is when I'm increasing. It would also be from 4 to infinity. And these regions should look familiar, just in different places from where they were on the last problem we did. Concave down would mean the derivative of the graph that I'm given is negative. It means it's going downhill in this picture that I'm given. So this should be from negative infinity to negative 5, and then also from 2 to 4. Okay, so again, different things can be found. Well, the same things can be found, but just in different ways, whether I was given the graph of the function or the graph of the derivative of the function. And actually, we can go even further. They can give us a graph of the second derivative of the function, and we can find still a lot of the very same things. Okay, let's look at these. All we're asking for now, though, are points of inflection, concave up and concave down. Remember, points of inflection are when the second derivative equals 0. Well, again, I'm given here a picture that has the second derivative. So for the second derivative to equal 0, it's just where it crosses the x-axis. So that's at the points x equals negative 5, 0, and 4. Okay? Concave up and concave down. Well, that means that the second derivative is bigger than 0 for concave up, it's positive, and the second derivative is less than 0, or negative, for concave down. And again, the picture that I'm given is of the second derivative. That means that I just need to look, when am I above the x-axis? That means that this graph, the second derivative, is positive. So those intervals are negative infinity to negative 5, from 0 to 4, and from 4 to infinity. Concave down means second derivative is negative. This picture again of the second derivative, it's only below the x-axis in one spot, from negative 5 to 0. So those are your regions of concave down. So hopefully this helps clarify a little bit about how we can analyze the graphs of both f of x, f prime of x, and f double prime of x to find the various pieces of information that we might need. Anything from extrema, critical numbers, points of inflection, concavity, increasing, decreasing, all of the above.